Hey, 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 good afternoon and happy Wednesday. Wednesday. You're getting this on Thursday, but that's no big deal. I'm doing it on Wednesday for you for tomorrow. Let's go back to our trivia question. We had a couple of good guesses. We had Dr. Furman, we had Mr. Wiseman. We even had someone say Mr. Ross, which is pretty cool because I don't know where that came from, only because I know that if you can know our science teachers, there are two that have been involved in EMT and firefighting, and that is Dr. Furman and Mr. Wiseman. Well, this young man is Dr. Furman, avid hiker. Here he is in his fire gear. I'll point out that is his buddy John. He's from one of the tower ladders in Ossining, and Dr. Furman would trust John with his life because they fought many fires together. That's pretty dang good stuff. Let me show you one more video, because here they are actually dragging Dr. Furman out of a building. By the way, a lot of you guys did get fast, and I forgot what it was. Once you guys said it, it was fire and search. What is it? Search team. I gotta look it up. Give me a second. Anyway, there they are dragging Dr. Furman out of a burning building. So this is what the training was for, to show you that if a fireman was unconscious in a fire and they have to get him out, this is the safest way to do it. They actually drag him down a ladder on a stretcher. So there's a little bit of education into firefighting from the Ossining Fire Department. Let's get started with our lesson today. I'll just come on and say hi. Doo-doo-doo. Hey guys, this hair is getting long. Dang it. Woo. This is crazy. Guys ready for a good lesson? This one's good. You're also going to be participating also, so we'll get to that in a second. Let's see here. Where are we? Talking about... Where are we? Talking about... Let's get to the notes. Oh, it's right here. Perfect. All right. Great. You're on this page right here. This is page 1, 2, 3, 4, 5. That should be 5. Why does this always happen? Come on. Okay, so that's 5. Just skip. I am not starting the lesson over again. Jeez. Start it. Boom. Well, let's start that over again. Let's get the file. I'm try it over here. Okay, so you're on page 1, 2, 3, 4, 5, 6. You're on page 7. Now we finally find out the last information about the last physical quantity we measure in the big 6. By the way, I stole the big 6 from Mr. Burbid. That's a pretty good way to do it. Your big 6, right? And we've gone through them. Amplitude. We did amplitude. Then we did frequency. Then we did period. Then we did wavelength. And we did phase. That was 5. And then number 6 is the last one, and that is speed. That's what I'm going to do right now. So let's choose our colors and get this party started. Let's see. All right. Get this party started. Corona, you ready for this?
I wish I knew the answer to that.
I wish you did also. Color time. What are we going to do? Let's do a nice color. Let's go with, I like this purple here. I like the calligraphy pen. So nice. Go calligraphy. Doo-doo-doo. Let's go with that blue. Crayon. Crayon haters out there. Let's see. Go with silver. I like the silver. And of course, we have a highlighter. Okay, so we need to know the relationship between frequency, period, wavelength, and speed of a wave. Let's look at that. Super important here. Oh, here we go. All right. Big note. Big note. The velocity of a wave is dependent on the, ready, wait for it, medium only. Dependent on the medium only. And here's your equation, so you can see how this works. And I'll show you some supporting demonstrations, actually videos, because all the stuff's at work, which is sad. Okay, so it turns out the V of a wave, and this is an equation for a string or a spring, okay? This is, all right, this is, so I'll put this here. This is going to be wave speed in a string or a spring, right? And it worked for most solid objects, right? Most solid objects. I think it should work for all, but usually we're just going to apply it to a string or a spring. Okay, so velocity is dependent on the square root of F sub t. F sub t is the tension, right? Now the mu, or me, if you pronounce it in correct Greek, this is not the coefficient of friction you're used to. A lot of times in physics we reuse symbols. We reuse symbols, and me is one of those ones we use several times. This is called linear mass density. That's equal to mass divided by length. Okay, so what does this tell you? Right? This tells you a couple of things. I'll put it right here, right? If you increase Ft, if you increase the tension, you increase the numerator, so that increases velocity of the wave. I'll call that V wave, right? This tells you, right, if you increase mu, linear mass density, if you increase that, that means you increase mass per unit length. And if you increase mass, remember that's in the denominator. You're increasing the denominator, that's going to decrease V of wave. So you see these questions here and see if you can answer them. Pause the video and see if you can figure this one out. Right? Will a wave travel faster through a rope stretched tightly? Oh, tight. First one hanging loosely. Right? So we know, how does tight tie into either tension or linear mass density? Now you might say, oh, well, if I'm stretching a rope, I'm making it thinner. No, it's not like a rubber band. All right? This is a static rope, kind of like they would use for rock climbing. So when I say static rope, you won't change. Stretching it, right? I'll make a note. Oh, no, not with that. Undo. Okay. Okay. Note. Stretching will not make it much thinner. Ooh, that's bad handwriting. I haven't written for a couple of days. Let's rewrite that. It looks horrible. All right. Try that again. Stretching will not change. Let's say it this way. Thickness. I like that better. Okay. So what'd you say? Will the wave travel faster through a rope that's stretched tightly or one hanging loosely? Well, let's reveal the answer. Tight rope. Dun, dun, dun. Since more tension increases speed. Oh, we're running out of. Let's go to my surgical. All right, surgical. Come on. I don't want to erase my word stretching. There we go. Leave it like that. Okay. And I'll show that to you in videos in a second. Well, let's do it now. This way you see it. So that's tight, stretching, more tension. So I found some pretty good videos. Let's see what we got. It's right here, right? Okay. I think it's the first one. Okay. I like the way this guy talks. It kind of messes up. Hey, listen, he's like me. He's not a guy that, that will record 20 times.
This is a demonstration
Here we go.
of wave speed on a rope. The wave speed depends on the tension in the rope in an inverse relation, in a direct relationship, actually. So if we don't have much tension in the rope, the wave speed...
It's not really direct, remember, because it's a direct... The speed is directly proportional to the square root of the tension. All right? So doubling the tension would increase the speed by what factor? There's a nice bonus question. Put that in your notes somewhere. Like where you right where we were just writing. Put a little note. If you double tension, you'll increase the velocity by a factor of blank. What will you increase it by? All right, back to this.
Is fairly slow. But as we increase
I talked over him, watch. Okay.
In a direct relationship, actually. So if we don't have much tension in the rope, the wave speed is fairly slow. But as we increase the tension in the rope, the speed increases.
Watch this.
And then at higher tensions,
super fast.
And yet higher tensions.
Let's go back. That was cool. All right, low tension, watch. Come on, play.
But as we increase the...
Do it again. Hold on.
So if we don't have much tension in the rope, the wave speed is fairly slow. But as we increase the tension in the rope, the speed increases.
Watch this.
And then at higher tensions,
super fast.
And yet higher tensions.
Watch this. Bang.
The speed gets very high.
Notice, greater tension means greater wave speed. Okay, so that was that. So now, will a wave travel faster through a thick rope or a thin rope? Did you answer that one? Take a second if you didn't. Pause it and answer it. And then come back and get the actual answer. Hey, welcome back. Corona, you think they're enjoying this, or you think they're going crazy in quarantine?
Negative.
Oh, I asked you 2 questions. I bet you answered the first one. Are they enjoying this? Negative. Guys, the best we can do, just put up with it. We can get through this. Let's see. Okay, so will the wave travel faster through thick or thin rope? So a thick rope, remember, it's going to have a lot more mass in a certain length. So as a result, I'll go with the big erase. Come on. A thin rope, since linear density is inversely proportional to speed, right? And actually, I'm wrong there. Since linear density, since the square root of linear density, I'll actually put that. Since I'll put that. Ooh, yeah, let's do red. All right, here we go. Since the square root of linear density. Let's see who actually writes that. Since square root of linear density is inversely proportional. I'm running out of room there, so give me a second. Let's fix this. Put the blue. Okay, good. And I'll put this in red. Inversely proportional. Can you read that? I can't. Let's write that again. Yeah, oh, it looks much nicer. To speed. Well, here's a nice one. I talked about it. It takes more work to... Takes more work to move the heavier rope. Move the heavier rope is what it said. So it moves slower. Don't put that. Let's not put that. Erase that. You don't need it. Let's undo. And let's erase. Hold on. Yeah, let's get rid of this. Let's go with draw this in white. You don't need that. Don't worry about it. Just easier to use the equation. Let's go with white. Color, white, super thick. Here we go. Oh, look at that. Look, I love being able to hide. There we go. Okay. All right, now let's see a video that shows you thick and thin rope. Where are we? I was watching it. I found a really interesting video from the University of Madison, Wisconsin. And he did both. The tension and the thickness. But I like the first one I showed you better. So when I show you the second one, is it this here? Is this here? I think this is it. Yeah, check this out. All right. Come on, play.
I have here a long rope.
I like this guy.
And on one end it's attached to the wall. And I'm going to stretch it out. And many of you have probably done this with a rope or maybe a garden hose. And if I stretch it and give it a flick with my wrist, I can make a wave that moves down the rope. So let's do that.
You see
now,
it come
you see
back.
A curious thing.
I love that he's in a tux. I'm just gonna show you. Look, he's in a tux. Well, I think he's actually doing a demonstration for like families. Because if you go through this, it is a college. When you go through this, you see little kids.
Heavy rope, the light rope.
Oh, actually, let me show you let me actually show you what I'm trying to show you, which is what he's talking about. Here, watch.
Bigger. And
hold on.
Flex and comes back.
Hold on. Sorry, guys.
Because down at this end, there's a pulley,
Hold on, I just want to get back a little. Okay, hold on. Come on.
much bigger. And these ropes are under exactly the
Hold on, me.
lower rope is a half-inch rope, much bigger.
Here we go. Hold on.
Waves traveling on a rope.
Here we go.
You see over here we have two ropes. The upper rope is a 1/4-inch rope, very small, and the lower rope is a half-inch rope, much bigger. And these ropes are under exactly the same tension. How do I know that to be the case? Because down at this end there's a pulley, and the rope goes around the pulley. So they're being pulled with the same tension. But one rope is a
Next year, if you take college physics, you'll understand why putting a rope around a pulley will guarantee the same tension on both sides. But we'll get to that next year.
light rope and the other is a heavy rope. Now who thinks the wave will travel faster on the light rope on the top?
Raise your hand. Who
Who
thinks?
thinks it will travel faster on the heavy rope on the bottom?
Ah, look at these little kids raising their hands.
So
Don't they
most
know
people
physics?
think the light rope
Come on.
will have the greater wave speed. Now, to make a wave on the rope, I have to somehow start the wave at the same time on the two ropes.
It's cute. Watch
The
this.
way I'm going to do that
Good.
is to take a meter stick, and I'm going to hit the two ropes at the same instant. Now, you notice Mr. Lovell has put a couple of
Hey,
index
Mr. Lovell.
cards on the rope down at the other end. There's a red one on the top and a blue one on the bottom. And what you're going to see is as the wave moves down there, those cards are going to jump off the rope.
Ooh, look at
And
that.
the card
Let's
that
see.
jumps off first, obviously, is on the rope that has the greatest speed.
Ooh, let's see
So
this.
don't watch me. Watch the cards down there.
I wish they showed
and
you
I'll
the
tell
whole
when I'm going
rope.
to hit it. 1, on 3, 2, 3.
That was pretty cool. Wasn't that cool, Caroni? That was really good.
Totally.
Yeah, totally. You are right. Okay, do I have another one here? Have another one? Yes, I got one more to show you because this is something I want you to do for extra credit. This is really good. Is it this here? All right, yeah. First of all, I wanted to show you longitudinal waves that I hadn't shown you past. I showed you a video a while ago, but this one is so much better. So I want to show you this quick. This guy did a really nice video of longitudinal waves. So check this out.
Okay, in this demonstration, we're going to look at longitudinal waves. Most of the...
Oh, great. I was trying to stretch it out. Sorry, guys.
Okay.
Okay. Play.
In this demonstration, we're going to look at longitudinal waves. Most of the diagrams of waves you've seen so far have probably been transverse. This
Yep.
is the classic sine wave
that.
that gets drawn on the chalkboard up and down and
True
back.
Why am I saying
And that's
true
a
that?
useful diagram, but it doesn't illustrate very well how sound propagates through the air. Sound propagates through the air as what's called a longitudinal wave. So sound is not going up and down. Sound is propagating through the air
Yes, check
through
this out.
air
This is cool.
molecules. That, if you can imagine
is
all the
cool.
molecules.
All right, we've seen this right here. We're going to watch. So he starts tapping on
Imagine
one side. Look at
each
this.
little wire of the slinky
Can you see the slinky
representing
hanging
an
there?
air molecule.
It's cool.
What I'm going to do is start
Yo, that is
vibrating
so cool looking.
one end of the slinky.
Dang it, that's
And
nice.
you can see
Look at
that the one wire bounces off another, that bounces off another, and ultimately propagates that energy down the length of the spring.
So there's your longitudinal wave. The wave is traveling to the right on the screen, and those coils
This
are
is what's called a
vibrating left
longitudinal
and
wave.
right. You can see them shaking left and right.
And this is a much closer
That's
example of
pretty cool.
how sound propagates
That
through the
looks
air.
good. Okay,
Keep
so
in
this is where
mind,
the
though,
extra
that
credit
sound
comes in.
propagates equally in all
Hello.
directions.
Quiet. This is where the extra credit comes in. I want you guys to set something up like this, either on a table, right? You can see here. I'll show you. Here's a nice slow-mo one. I'd like you to do this on a table. You don't have to draw at a table. You don't have to draw direction of wave and direction of vibration. Let me just lower this because you don't need to hear the music. Okay, so here's what I need you to do. This is where the extra credit comes in. If you have a slinky at home, obviously you can do this. So you have to have a slinky. Oh, come on. Jeez, you don't play? Okay, here we go. Okay, so watch. What I'd like you to do is time how long it takes that pulse to move across the table, right? Time how long. And then, now he doesn't do it in the video. What I'd like you to do is stretch the slinky a longer distance so you put more tension in it. Then time how long it takes to get across. And then if you have a tape measure, calculate the speed of the wave. And of course, how you would do that, you measure distance, how far the wave traveled, you measure time, send a video to me, and then tell me, and if you don't have a, hey, listen, actually, let's make this easier. If you don't have a tape measure, no big deal. All right, send me a video of you timing 2 pulses, one when a slinky spring is not under a lot of tension, and then one where it is. All right, So you could do that one of 2 ways. You can keep the spring the same length, but just make it tighter by holding more coils in your hand. That'll make the rest of the spring tighter, or just stretch it down the table a farther distance. All right. So either way, send me some. It'll be pretty cool. All right, pretty cool. I couldn't find a video that showed that, so unfortunately, I can't show you that. And of course, if we were in school, I would do this. All right. So that's what velocity is dependent on. Come on, scroll up. There we go. Now the equation that I like to call Flambda. Yes, Flambda. Let's talk about this. Okay. Since the length of one cycle, right? The length of one cycle is called lambda. That's your wavelength, right? The length of one cycle is the wavelength. That is wavelength. And the time for one cycle is the period t. That's your period. If we want to calculate the velocity, we got to take v and divide it. And we got to take v. Well, if you want to calculate v, you got to take the distance the wave travels and divide it by time. Where did that go? Why does this stuff disappear as I don't get it? It's like period disappeared. I don't understand why when I try to erase over here. Okay, so V, again, why are you doing that, dude? Holy jeez, let me try locking this down because something's going on. Is there, let me, actually, hold on, let me see something. Pointer, move this. Is there something there? Give me a second. I think there's something here. Like a little bit of white. Now it's gone. Cool. Okay, let's move this back. Oh, you gotta be kidding me. Come on. Pointer. Point. There we go. Okay, let's try this again. All right. To calculate velocity, you gotta take d over t, right? But wait a minute. Remember, d is wavelength. Time is period. So you're really taking lambda over period. Now, believe it or not, that's an important equation. I want you to put a box around this. And you're going to write this on your reference table. On PRT5. PRT5. You're going to put it next to the next equation we're going to derive right now. Now, remember, V equals lambda over period. But that leads to V equals lambda over 1 over the frequency. Remember, T equals 1 over F. So we're substituting 1 over F in the denominator. Now you have... I'm just entering a competition to win $1,000. I love it. And I'm entered. Woo! Okay, good. All right. So there's your equation. Lambda over 1 over frequency. That's a complex fraction. Complex fraction, you should know, when you divide by 1 over F, that's the same as multiplying by the reciprocal. Well, the reciprocal is F. Here's your equation. V equals Flambda. That is how I say it. Flambda. There's your 2 equations. So if you go on to PRT5, Party 5, pretty sure it's Party 5. Let's do physics reference tables, physics, Regents. Can I spell? Physics, Regents, reference table. There we go. All right. So if you're on that, this is PRT1, PRT2, PRT3, Party 3, Party 4. Here's Party 5. Okay, so right over here, you see right at the top, it says V equals Flambda. Put right next to it, V equals lambda over period. Very important equation. I recommend having both. Have them both there. Okay, that's our equation. V equals Flambda. Now this tells us something really important. This tells us in a uniform medium, the relationship between F and lambda is, remember, in a uniform medium, make a little note, in a uniform medium, V is constant. And of course, that's V wave. V of the wave is constant. If the V of the wave is constant right here, that means you have an inverse relationship between F and lambda. If that F goes up, lambda goes down. Nice inverse curve. Okay? Nice inverse curve. So that's some important notes there. Remember, now you know what affects everything. So we'll do that on the next page when we go over something, when we go try a problem. But remember, we talked about right here, boom, speed depends on medium, right? The velocity of a wave depends on the medium. You don't have to highlight it unless you want to. Velocity, dependent, medium, all right? So velocity depends on medium. That brings us back to something we did a while ago. Make sure you go back and write this in. Where was it? I think it was on the next page. Yes, right here. Right down the bottom. You wrote this. You wrote wavelength depends on frequency and, well, you could put one of two things here. And some of you already wrote it. You could write either speed or you could write the medium. Either one. Speed or medium, right? And it's not just speed, but wave speed. I like to specifically say wave speed. So it's either wave speed or medium. And a couple of you guys got it already. I'm impressed. Right? Dana Lucas, I think you were one of the first ones to get it. You know, that was good. You know, you looked at the equation, went, oh, V equals Flambda. Many people saw that. A couple of you did. I'm sorry, I don't know everybody. V equals Flambda, and you knew, oh, if F depends on source, right? And this depends on medium, well then lambda depends on F, and that's supposed to be an F and V. Okay? You don't have to write that down. I mean, you already did it, so you don't have to do that. Let's get rid of all that. There we go. Boom. Goodbye. What's written there? Oh, no, right. Oh, that was the equation. Did I ever not write? I didn't write that equation down. Are you kidding? I thought I did. That's great. Let me write that. Since you're here, might as well write it. All right? Let's get rid of that. Boom. Lambda equals distance over cycles. There we go. Thought I wrote that down. Okay. Ready to try one all-encompassing problem? Finish this all up? Let's do it. You guys, of course, can go and try it on your own, as usual. Pause the video, try them, and then come back. All right? And there's an extra piece we have to do here, and that's this here. You'll see what it says here. I think it's written on your handout. I think I fixed it. Or I didn't because you don't have the actual handout. Two of you do. The rest of you made a copy from the PDF. I forgot if I wrote it there. It might be there. I'm not sure. Okay. So we'll get to that last. Right? So you guys try this problem. And in fact, I would wait on this piece. Let's do this one together. Okay? The one I just highlighted. You guys try 1 through, 1 through 11, and then come back. How you think you're doing, Crone? You think they're doing a good job?
No.
Oh, man. All right, let's get going. Welcome back, guys. Amplitude. Remember, amplitude is displacement, is max displacement. And I'll make notes. And I'm going to make a couple of things here. So we have max displacement from middle, from equilibrium, or middle. I'll just say middle. Right? Okay, so middle is, here's your middle. Here's your max displacement, and that's going to be 0.01 meter. All right? 0.01 meter should be written right over here. Yeah, look at that, 0.01 meter. Okay, now we're going to go through a whole bunch of stuff here. Again, I want to change my color. Actually, we'll do that after. I want to go through what everything depends on. We'll do that after. Okay, so I've given you number 2 and 3 to show you a difference in how questions are asked. Notice one of them says number of wavelengths, and one says the wavelength, okay? When they say number of wavelengths, this is a counting number. You have to count wavelengths. So we go and look, right? I'll change colors as I go through this. So the first one, I'll use the crayon. Now I'll use the crayon. Yes, okay. So I'll do the first one in this red. So let's go. You guys tell me when to stop. One wavelength. Let's see. Oh, wait, should I have stopped there? I thought I heard one of you say stop. Should I have? Let's back up. All right, let's do this. Coroni, should I stop here?
Why not?
No, not. Don't. That is not. Here we go. So I would color this with different colors. So here we go. There's one wavelength. That's counted one wavelength. Let's change this to blue now. All right, let's do a second wavelength. Here we go. Here's the second wavelength. Make sure you get some crayons. Do this. Okay, look at that. There's the second wavelength. Right? So that's two wavelengths. All right, let's do one more. I'll do this one in green. Here we go. Now notice, we get shortchanged. Dang it, we only got half. So that is a counting number, as I just said. And instead of saying number with the number sign, let's write this counting number. All right, how many did we count? 1, 2.5. All right, so the answer there is 2 surgical. Here we go. Hello. Actually, let me go back a sec. Right here. Hold on. Give me a sec, guys. Let me move this up. Come on. Go. No, come on. Move. It's not hard, guy. Come on. Seriously, bro? Were you telling me you locked? Oh my gosh, it unlocked the wrong thing. Give me a second. I love playing with this. Here. Oh, now you move, buddy. Thanks. Okay, that's counting number. Back to this. Yep, so we got 2.5. Now notice, we're going to put it in short terms. You could write it as 2.5 lambda, or you're saying 2.5 wavelengths. Now, that's not the same as the wavelength. As soon as it says what is the wavelength, you got to realize wave, even though it's one word, the wave part is an adjective, right? Number 2 asks for a number. Number 3 asks for an actual length. That's why I'll make a note. This is not a counting number. It's an actual length measurement. It's an actual length measurement. So when you check, you can see, oh, look at this. We have a ruler here that says, you'll notice it says 4 meters right here, and it says from here to there. Oh, okay. So you got to realize how many cycles are in that length. So we go right with our equation right here. We have wavelength equals distance over number of cycles. And I'm going to do this one a different color, just so it, because, I already done it here. We'll leave it, cycles. Distance is 4 meters, but realize you're jumping from 1 to 2. So we have 2 cycles in our drawing. So 4 over 2 is going to be a wavelength of 2 meters per cycle. Okay, so that's a wavelength. Period. Well, this one's kind of easy. I love when they give you numbers for every cycle. Remember, period is going to be, period is time. Well, actually, I'll write it out. Period equals, put it right here, time over cycles. So look right here. Boom. Oh, no, not that color. Highlight. Look at this. What do you notice here? Oh, they told you it's 0.4 seconds for one cycle. That's the time after that red cycle I drew. So really, that's actually a really easy calculation. 0.4 seconds for one cycle. Done. There you go. There's your period. Because it's the time for one cycle. Frequency, though, you can do this as the reciprocal of period, or just put in your equation. Frequency equals cycles over time. Now, you can do, I always like counting everything we have there. Or you could go with just the 2 cycles there. And that's where you could pick any bunch of numbers. I usually just count what we have there. So I see we have 2.5 cycles, right? Total cycles. But that time, which is not written in, I got to go right in. That is, it's 0.2, 0.4, 0.6, 0.8. It's 1.0 seconds. Huh. Oh, wow, that was easy. 2.5 cycles per 1 second. 2.5 seconds per second is 2.5 hertz. There is your frequency. All right, scrolling up. Frequency. Seriously, what just happened? This thing was not locked. Hold on a second. Okay, let me try to lock this. No. Stop. Let me lock it. There we go. Okay, sorry guys. Okay, now we can scroll up. Oh, now we got velocity. Yay. Okay, got one of 2 things you could do. All right, you want to do Flambda? Well, we already, see, we have several things. We have lambda already. Right, so highlighting, we have lambda. We have period. We have frequency. So you have a choice of 2 things. You can go with V equals Flambda. I'll do both. V equals Flambda. We have a frequency of 2.5 hertz and a lambda of 2 meters per cycle. And you'll see, 2 times 2.5 is 5. Wait a minute, what's the unit here? 5 hertz meters. What the heck is a hertz meter? Well, remember something, I'll put that over here. 1 hertz equals 1 cycle per second. But in reality, the cycle is like radians. This is not a unit. So really, this is really 5 meters over seconds. Now, that's one way to do it. Or you could do the other one. You could do lambda over period. Or V equals lambda over period. Lambda, again, is 2 meters. But the period was 0.4 seconds, right? And 2 over 0.4 should be, because remember, 4 is 4/10. So 2 divided by 4/10 is really 2 times 10 over 4. That's 20 over 4. Yeah, there's your 5 meters per second. Okay. So there are your mathematical calculations with the big 6. Look at that, the big 6. We did 1, amplitude. 3, wavelength. 4, period. 5, 6. Let's see. So wait, where's my big 6? I got amplitude. Oh, we just didn't do phase. That's why. The big 6 is phase. Number 6 anyway. All right, so if the frequency is doubled, what happens to the period? Oh, frequency doubled, period would be, they're inversely related, right? Frequency doubled, that's going to be cut in half. They're inverse. They're inverses, right? So now frequency is doubled, what happens to the new wavelength? Oh, wait a minute, guess what? Don't forget, cut in half also. They're also inverses, right? Ooh, if the wavelength is double, new period would be, well, hold on. The equation here, where for the first one, it was T equals 1 over F, and for the second one, it was V equals F lambda, right? Wavelength doubled in period. Oh, that equation could be V equals lambda over period, all right? So, hold on a second, scroll. Come on, scroll up. I gotta be careful. I want to add something here. And you might want to add this too. They'll tell you, if the wavelength doubles in a uniform medium, they have to say that. They usually, sometimes they won't. A uniform medium. What that means is, uniform medium means constant V. So if this V is constant, right, you get a constant V, notice there's a direct relation between lambda and period. If lambda goes up, period goes up. Lambda up, period up. So if wavelength doubles, period would be double also. All right? Here's where I put the medium word in. Say medium. Speed, no change. B would stay constant. Stays constant. stays constant. And lastly, increase energy of water wave. Okay, now energy, remember, what is energy tied to? Energy is tied to the amplitude of the wave. Amplitude. All right, and I think we have a couple more here. We'll try some of the mathematical ones on the front page. Do I want to add those things that I said to add a second ago, which was what? Nah, I think the notes will get all too confusing. We're good. Or should we put it right? Oh, no, we'll sum it up on the other side. I think we're running. Yeah, perfect. Okay, good with this. So go to the next page right here. Let's do these last couple of problems. So these are your mathematical type problems where you can do a so we to swoo. Let's see, changing our colors, go with the blue. Okay, so we have a wave with a speed. Oh, here's V. We have a V of 0.25 meters per second. All right. Now notice, this is where things get interesting. It says it causes a cork to move up and down in the water 4 times in 8 seconds. 4 times in 8 seconds. And they want you to get the wavelength. Okay, so wavelength is our unknown in meters per second. So you should look at this and go, I have V and I have lambda. I'm sorry, I have V, I need lambda. What equation ties them together? What EQ ties V and lambda together? And you can use one of two. You can do V equals Flambda. Now remember, V equals Flambda requires a second step because frequency is cycles over time times lambda. So you gotta watch out for that one. So many of you would probably say, you know what, I'd rather get the frequency first. So I'd go 1, frequency equals cycles over time, which equals, what is cycles? It was 4 cycles. I said 4 times, 4 cycles, in 8 seconds. 4 over 8 is a frequency of 0.5 hertz. Now 2, use your V equals Flambda equation. Yes, I like saying Flambda. V equals lambda, and we have a V of 0.25. I already wrote my knowns and unknowns with units, so I'm good. F is 0.5, I just wrote it there. 0.5, and then we need lambda. Okay, so we got to get the numbers right. So what is 0.25 divided by half? Oh, so lambda has to be 0.25 over 0.5, which gives us a lambda of, my lambdas never look very good. Let's make those lambdas better. There we go. Lambda's going to be a quarter over half. Why am I writing 0.05? Hold on. Surgical. Yeah, we got surgical. Let's get rid of that little tiny. There we go. And just change with my, there we go. So a quarter divided by a half is the same as multiplying by 2. That's going to be a 0.5 meter. Don't forget, the unit is meters for wavelength. They're not asking you to count cycles. They're asking you for the wavelength. What is the wavelength? Not number of wavelengths. Okay? So there is your V equals lambda. And then number 13. Surfacing whale in an aquarium produces water wave crests having an amplitude of 1.2 meters. They gave you some nice, useless information. They gave you 1.2 meter amplitude. I don't even need it. But notice what he says. It says one wave crest. Okay, produces wave crests every 0.4 seconds. Ooh, guess what they just gave you? By telling you wave crest every 0.4 seconds, changing my color to the purple, they just told you right here, they just told you the period equals 0.4 seconds. That's because they're making a wave crest every 0.4 seconds. That means they're making a wave every 0.4 seconds. So that really is seconds per cycle. And it says the water travels at 4.5 meters per second. Water wave, they give you V of 4.5 meters per second. All right, 4.5 meters per second. And lastly, that would be, where is it? Oh, and they're looking for the wavelength, lambda, right? The lambda in meters. Now, this is where I'd rather not convert period to frequency. I'd rather just use my other equation I wrote on PRT5, lambda over period. lambda is, oh wait, we're trying to get the wavelength. So if you do that, hold on, lambda over period, you have to plug in. That's 4.5 equals lambda over 0.4. Multiply both sides by 0.4. 0.4 is 4/10. So that's going to be, I can't do math in my head right now. And of course, calculate, here it is. What do we have? So we have 4.4 times 4.5. Boom. We have 1.8 for lambda. Lambda equals 1.8 meters. Boom. Boom. All right? So before we move on, now, if we were in class, we'd actually be having a test on everything through this page. So I got to think about that. I think we might have to have some kind of test to have a little fun with this. We'll figure this out. All right? I'll let you know. But back to this page here. Oh, I want to add just one more thing. This will be the end of this topic, at least the first part of waves. Okay. So let's do just quickly. Okay. Final summary. Remember, 1, go through them. Amplitude depends on blank. 2, frequency depends on blank. 3, period depends on blank. 4, wavelength. Before that, probably better if I write speed. 4, wave speed. Let's try it again. 4, wave speed depends on blank. Then, bam, wavelength depends on blank. That's your 1, 2, 3, 4, 5. The last one's the hardest. I wanted to let you guys look that up as a bonus. Phase depends on. So they won't ask you that, but it's a really interesting thing. And it might be several things. So I'll leave that up to you to find out. So you've now tied together the big 6 and how they're related mathematically. I'm going to assign a castle. And you guys can have fun with that. And don't forget, I need that video of you vibrating a slinky spring as a longitudinal wave under different tensions so we can see the difference in speeds. Hope you enjoyed this lesson. You guys have a great day, and I'll talk to you soon. In fact, wait a minute. This could be the last lesson of the week. For those of you taking APs next week, best of luck. Take care. Bye-bye. Say goodbye, Karoni. That's not goodbye.